All right, got a few questions regarding the Organic 1 homework. First one being question 55. So question 55 gives you an IR spectrum. And yeah, we're just going to kind of crudely draw it out here. But it asks you which compound corresponds to this particular IR spectrum. So with IR, the thing here is that you have to memorize. There it goes. The thing you have to do is you don't need to be memorizing these tables as to what the IR bending modes are. Those are provided for you. So if you go to the course website, under actually underneath the exam itself at the very top, there is a link that gives you a list of common proton chemical shifts, carbon 13 chemical shifts, IR bending modes, and it also gives you the dielectric constant of the solvents, but we're not there yet. So if you look at the common bending modes, these little scribbles right here are generally ascribed to CH bending modes. There's lots of variants of them. So what we're not seeing with this, because it gives you a few options here, it gives you an ester. It gives you a ketone. Oh, aromatic ring there. And I'll draw it the way they've got it drawn. An ether. And then just this alkane. So if you look at the bending modes that are present in that table, each functional group kind of gets its own bending mode. So CH3, CH, CH2s, all your alkanes sit in this region. This phenyl ring here is going to have some bending modes close to, I think it's the 6 to 700 range. And this is due to ring breathing, and you're also going to get both modes associated with this ester, specifically this carbonyl oxygen. So this is why I got you to memorize the functional groups at the beginning of the semester, is that you'll know what these functional groups are and what it refers to in that table. So if you look at the table, we don't see bending modes to this, we don't see it to this, and we don't see it for ether, nor do we see it for the phenyl group. So really the only one that survives here are the CH bending modes. Now I'm going to submit that as my answer and be really embarrassed if it's not correct. It is not. Hold on. What other bending modes are there? So let me see what I'm missing. Yeah, it's table of common 1H13C and IR values. You know, I bet you that's a ketone mode right there about 1700. Sorry, I gotta give my computer just a minute, especially when it's opening up Word. Actually, let me share my desktop with you. So we've got all these IR bending modes. And, sorry, that's carbon 13. We got all these IR bending modes, and I switch over to the software. I've got my little peaks around 3000, and if I look at the 3000 range, I'm seeing, here you are, the CH bending modes. So sp3, sp2, sp, these are all kind of there in that range. So that's there, but we are also seeing a peak around, looks like about 1700 wave numbers. So the sharp peak down here. Now keep in mind, everything beneath 1000 wave numbers, everything beneath 1000 wave numbers is the fingerprint region, so we're not going to worry about that. So if we look for a peak about 1700, we've got aldehydes and ketones here. So that's a real possibility. If we look in this peak, we've also got peaks about 1200. Hopefully that's something unique. And I've looked in the 1200 range. I'm not really seeing anything in this other than the CO with the sp2. The CO sp2 here is referring to carbonyl carbons. The sp3 here is referring to alcohols. So I see another ketone bending mode. And there's a little bit of mess between around 1500. And if I take a look there, I don't really see anything corresponding to that range. Now, how about carboxylic acids? Well, if it's a carboxylic acid, we should see a binding mode about 1700, 1725. And we don't really see that. Like, there's no peak sitting in that region. So I'm going to make it do this. Show me solution. So here it tells you you've got the carbonyl peak, and the 1200 allows the compound resistance, so the compound most likely is, and of course it's not showing it. The compound here, I'm going to guess here, is this ketone. So let me redo the problem. Oh, you're obnoxious. That's what I get for being lazy and not actually checking all the bending modes. That's odd. It's definitely not an ester. Okay, let me take a look at that question because I don't understand why it's claiming that's an ester because I'm not seeing any bending modes here due to the aromatic ring here. So if you're curious what the answer to question 55 is, it's this benzene ring attached to an ester. But I don't agree with them. So, sorry for that. Question 56. Oops, sorry, wrong one. The base peak appears at mass charge ratio 105 for the following molecule and 119 for the other two. Match the compounds with the appropriate mass charge value with their peaks. So compounds that have peak at 105 are. So when it comes to mass spec problems, we have to kind of figure out what the mass would be for a given fragment. So these are the three fragments they give me, and they say there's a charge of 105 and 119. So let's start taking a look for peaks that look the same. So 105 here. So let's start breaking these things up, and let's start clipping groups off the benzene rings. Base peak appears 107. Well, so these all weigh the same thing. They have the same number of carbons. The question is, can we clip a fragment off and get the same atomic weight? So if I clip the methyl group off here and here, I've got 6 carbons, so that's 12 times 6, 7, 8, 9, plus 2, 4, 7 hydrogens, plus another 1, 2, 3, 4. That's 9. It's 108. It's 11 gives me 119. So if I clip the fragment here, this would weigh 119, and this would weigh 119. So this would be 2 peaks that would give me 119. Now, if I took a look at these and I clipped one, let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 12 plus 3, 6, 7, 8, 9, 11. It's also 119. So what's the difference between 119 and 105? That's 14 AMUs. Or a CH4, a CH2 group. So how would we have a molecule that has a CH2 group clipped off? Fourteen AMUs, carbon and 2 hydrogens. I only see one that has a CH2 group on it. And that would be compound B. So let's see if that's right. So this difference of 14 AMUs would correspond to having a CH2 group that could be removed. And there's only one compound in here that has a CH2 group. So the reasoning here is that if we clip off a functional group, which we typically do with mass spec. In this case, we would clip off a CH2. There's only one compound here that actually contains a CH2, so that's why compound B is the only one that has a peak that appears at 105, because it's the only one that has a CH2 group that can be lost. Whereas the other two compounds have peaks at 119 because they don't have a CH2 group to lose. All right. Question 58. How many rings are present in the compound CH12? The ring consumes 3 moles of H2O catalytic hydrogenation. And please answer your question in the provided box. So this is going to lead us into alkanes. It's also going to kind of help with this predicting the number of possible isomers for a given, constitutional isomers for a given chemical formula. So we have the formula C8H12. Now, a formula for an alkane, C4H8, is CnH2n plus 2. So for C8, a saturated hydrocarbon with no double bonds, no rings, is C8H18. So if we have C8H12, we are deficient 6 hydrogens. Now, the 6 hydrogens can be lost 2 ways. Each ring, for each ring we would subtract off 2 hydrogens for each pi bond. So this would be a double bond or a triple bond, we would subtract off 2 hydrogens. So since we have 6 hydrogens, we have the potential to create 3 pi bonds or create 3 rings. So how do we know how many we formed? Well, that's where our 3 moles of H2 comes in. If we have pi bonds, we can eliminate them with H2. So each mole of H2 that's consumed equals 1 pi bond. So since we have 3 pi bonds, since we have 3 moles of H2 consumed, we have 3 pi bonds. And that would tell us that we have 6 hydrogens lost in our chemical formula just due to those double or triple bonds. So in this case, we would have 0 rings. And the reason we have 0 rings is that every deficiency in hydrogen here can be accounted for by a pi bond by the hydrogen absorption. Now, if for whatever reason we had C8H10 and we had the 3 moles of H2, well, our 3 moles of H2 would tell us that we have 3 pi bonds, but we need one more reason to explain why we don't have enough hydrogen, so that would be 1 ring. All right, question 59. Compound of the molecular formula C8H9NO2 has peaks for its benzene ring carbons at chemical shift 113.8, 119.3, 131.6, and 151.4. Now there are peaks in the benzene ring residue. Which compound is most likely consistent with the carbon-13 NMR? So what we're looking for here is symmetry. Now these are all reasonable chemical shifts. Well, let me drop the molecules first. Shift 13, 119, 131, and 151. Okay, so trying to think about the way to explain how to answer this. First of all, we need to make sure that there are only 4 unique peaks in this molecule, and that would be true. If you look at all the symmetry planes, for here we'd expect 1, 2, 3, 4 chemical shifts, because those are consistent. Those are consistent. These are not consistent, actually. So if you look at these, this one is closer to this amide than it is to the ester. So these aren't actually equivalent. We'd expect to see 6 unique positions inside this molecule. Same here, we'd expect to see 6 unique positions because there's no mirror plane in this molecule in terms of that benzene ring. That benzene, you can't go clockwise and counterclockwise and basically say, oh, they look the same. They don't. So we can eliminate these 2 off the back because we would predict these to have 6 chemical shifts in the benzene ring, not just the 4. So that leads us down to these 2. So the question is, which one's more consistent with having a strongly deshielded carbon? Now the 113.6 and 151.4, these are strongly deshielded. So my guess here is going to be this molecule here as being the unknown molecule. So let's see if I'm right. I was not. So let's see if it's the other one. So it's actually this one. But you can easily eliminate 2 off of the bat just by saying, like, we'd expect there to be 6 chemical shifts, not 4. And again, the 6 comes from the fact that there's no mirror plane here connecting the 2. So if we look at the benzene ring in terms of R and R prime, this has a symmetry plane. This does not. So then the next subtle nuance is basically determining, which one loses electron density stronger. So for that, I would say consult the chemical shift tables. Now I did get asked about the exam itself. 25 questions, I believe, for both Chem 1 and Chem 2. You get 75 minutes to complete the exam. There's also anti-cheating measures in place, so do make sure you're being honest when you take this exam. Have not checked the chat yet. How to explain chemical shifts. I just closed that tab. So just got a question in the chat. Can you explain chemical shifts like number 45 and enantiomers versus diastereomers in general? Okay. So question 45. Let me load up the homework for Organic 1. Hey, actually, now to do this one. So we've got this molecule. goes A, B, C, D, E. And it gives you a list of chemical shifts, 1.6, 4.0, 7.5, 8.2, and 12.0. So again, this is where your functional group's going to come in a little bit handy. Carboxylic acids, these are going to be the most deshielded protons. Now, if you're looking for kind of a guideline as to where these would sit, download the tables off the course website. It'll give you the chemical shifts for things like alcohols and carboxylic acids. But definitely proton E here is going to be your biggest deshielded, simply because it's sitting next to an oxygen. It's as deshielded as you can possibly get. Now, something like B, a methyl group, we expect this to be pretty shielded. And A, we expect to kind of be shielded, but because it's sitting next to this carboxylic acid, it is pulling electron density away. So we'd expect this to be the second most shielded. Now, if you look up in your tables of NMR shifts, you'll see hydrogens associated with the phenyl rings are actually more deshielded. When you go into organic 2, you'll get to see why it's more deshielded. So in terms of picking C over D, we have to look at who's closest to an electronegative element. So C here is 1, 2 elements away from nitrogen. D here is 1, 2, 3, 4 atoms away from oxygen. So C we would expect to be slightly more deshielded than, C to be slightly more deshielded than D, simply because it's closer to an electronegative element like nitrogen, versus D, which is closer to carbons, which are less electronegative. So let me drag them down. And verify what I just told you is correct. So I get B, A, D, C, E. When I check my work, it tells me I'm correct. All right, so enantiomers versus diastereomers. And we'll put meso compounds in here as well. So enantiomers are related by, so if we have a chirality, so to have an enantiomer, we have to have at least one chiral center. So enantiomers have at least one chiral center. And for two molecules to be enantiomer, the symmetry of each chiral center must be flipped. So what this means, if we have a simple molecule that has it has just one chiral center and it's R symmetry, its enantiomer has S symmetry. So if you have a molecule with one chiral center, it has an enantiomer, and the enantiomer is just the molecule with the reverse symmetry. Now, for diastereomers, we need at least two chiral centers. So if we have a molecule that only has one chiral center, it can't have any enantiomers. It doesn't have enough. So it has to have at least two chiral centers. And for two molecules to be diastereomers, at least one, but not all, chiral centers have to be flipped. So in the case of two chiral centers, if we have a molecule that is R at both, its enantiomer has both chiral centers flipped. So if it's RR, its enantiomer is SS. In order for them to be enantiomers, we have to flip at least one, but not all. So in this case, the only thing we can do is flip one. So for an RR molecule, its diastereomer is one that is SR or RS. For the SS, it's the same way. It either has to be RS or SR, but it can't be both flipped, otherwise it ends up being its diastereomer. And this becomes even more pronounced if we have three chiral centers. So let's say we have three chiral centers, they're all R. The enantiomer is the SSS. A diastereomer is anyone where we changed at least one but not all. So we can flip one chiral center, or we can flip two chiral centers, but we can't flip all three. So a diastereomer of the RRR would be RSS, SSR, SRR, RRS. Any of those combinations, so long as we haven't flipped all the chiral centers from one symmetry to another. Now, meso is a special case where we have a symmetry plane running through the molecule, and all the chiral centers, so let's say I had something like this. This molecule has two chiral centers. If I have a mirror plane running through the molecule, we have an R, and that mirror plane is going to give us the S. So for meso complexes, because we have this mirror plane running through the molecule, we end up not having an enantiomer because the mirror image of this molecule is just this molecule. So the way to think about a meso complex is that it's its own enantiomer. Just because of the symmetry of the competing symmetry groups, the R and the S here, so one's R, one is S, they basically cancel each other out. So we'd have to have a mirror plane for that to work. But meso complexes can have diastereomers. So if we have one, let's say this is R and the SS and the RR forms are both diastereomers of the meso complex, and the RR and the SS are enantiomers of one another. It just happens to be that in this case the R and the S don't have an enantiomer because of that mirror plane. Now, cool thing about Fisher projections, and I do mean that unironically, cool thing about Fisher projections is that they actually make tweezing out the enantiomers and the diastereomers a lot easier. So let's say I have this molecule and it has two chiral centers. So I personally do not know what this is off the top of my head in terms of R and S. Well, by definition, the enantiomer is the mirror image. So for the Fisher projection to flip between R and S symmetry, I guess I can work it out real quick. 2, 3, that's S. 2, 3, that's also S. In order to flip R and S with a Fisher projection, all I have to do is switch sides. Switch the sides of the H and the OH. So if I flip things, I automatically flip the symmetry. So this would be R and S. If I flip this symmetry, I get R, R. And let's flip that. So I've got four possibilities because I've got two chiral centers. Now, if you look at it, I flip the S and the S and the R and the R. These are literally mirror images. So this is on the right side, these are on the left. Now I flip them. This is on the left side, this is on the right. So these two here are enantiomers. These two, S and R, if I take the mirror image, well, that's going to flip the H and the OH. I think I drew the yeah, that was a mistake on my part. If I draw the mirror image, the H is going to be on the left side, the OH is going to be on the right side. So these two are enantiomers. So here I've converted both chiral centers, SS to RR, SR into RS. The ones up and down, left and right, these are all diastereomers because only one has changed. Switch one S to an R, one S to an R. Yeah, glad that could help. question 30. Let me bring it up. Question 30. I'm going to leave off the hydrogens because they're applied. So we've got our methyl groups. And the question is, what are they? So we've got a mirror plane here, which makes it meso. So I would argue they're the same things because all you've done is just taken it and rotated around this plane 180 degrees. So they can't be enantiomers because you can't have an enantiomer with a meso complex. Can't be diastereomers because you flip both compounds. They're definitely constitutional isomers because they're all bonded the same way. So yeah, I'm going to go with the same compound here. And that is correct. Now if you had this, because there's no mirror plane, drew the same compound twice. Yeah, these you could definitely not rotate into each other. So these two would be enantiomers. And both of these would be a diastereomer of what's given for question 30. Question 37. So the absolute configuration negative bromo, chloro, fluoro, methane is R. Which of the following is R? So first thing you need to do is figure out if it's what R or S would be. So he gives you four options. The other one, CLH. So the easiest thing to do with these is draw the associated Fisher projection for everything that is not a Fisher projection. So the way a Fisher projection works is that it's rotated in such a way that the bonds that are up and down go back and the bonds that are left and right come out at you. So this one we just need to turn it 90 degrees, and if we do that, we'll get F, Cl, Br, and H. For this one, you're looking at the backbone, so if we rotate it towards us, Cl, H, F, sorry, that's a Br. Same thing's true with this one. If we rotate it, we get H, Br, F, and Cl. Now, next thing we need to do is figure out the priority. So hydrogen is the lowest in all of these. We go by atomic weight, so hydrogen is the lowest, 4. And then we go by atomic weight, so bromine is the heaviest, chlorine, and fluorine. So with these priority groups in mind, we can start working out whether or not these are R and S based off their Fisher projections. Now, I would recommend you build the molecule so you can put the hydrogen back and see it. There is a trick that if you take the fourth group, erase it, and flip the other group over, this is the way it would look if you rotate it with the lowest atom back. If we look at it, we go 1, 2, 3, This is counterclockwise, so this is the S conformation. This doesn't work. For this one, do the flip. 1, 2, 3. Also counterclockwise. This is S. This one, flip the lowest group. BR 1, 2, 3. That's also S. For this one, flip the lowest group. One, 2, 3. Counterclockwise. These are all S. Why do I feel like I did something wrong? Fluorine, chlorine, bromine, iodine. R is clockwise. Rotate that 1, 2, 3. Yeah, that's S. Means I've drawn one of these wrong. One, two, three. That's counterclockwise. Every single one of these is counterclockwise. This is why you build the model. Okay, let's build the model. So the first one, if we build the Fisher projection, and we'll let, that's a good one, places the hydrogen. So since fluorine is yellow in the picture, we'll make this fluorine. Actually not. So, because I'll remember it, fluorine, chlorine, bromine. And this little happy one will be hydrogen. So for the first one, we've got the Fisher projection. So we've got fluorine going up and down opposite bromine. And then we've got hydrogen, chlorine, fluorine, bromine. So this is the Fisher projection as drawn for the first one. We tilt down, we go 1, 2, 3. Make sure I did that right. Fluorine, chlorine. Oh, nope, sorry. Chlorine, bromine, hydrogen. Okay, yeah, so that's S. If you look at it, that's S. So black here is highest priority, followed by blue, followed by yellow. If we draw it again, so we got fluorine, opposite chlorine, bromine, opposite hydrogen. So this is the second one, fluorine, chlorine, bromine, hydrogen. If we turn it so this way, lowest group's in the back, we get 1, 2, 3. I flipped them again. Sorry. This will also go counterclockwise. Tell you what, we're going to make fluorine red, so I'll actually remember it. Fluorine is red, bromine is black. All right. So in terms of the third one, we've got fluorine coming up, bromine going down, chlorine going back. We got the hydrogen. So now we look at it, we get bromine, chlorine, fluorine. This is clockwise, so the third one is actually R. All right, now for the last one, we've got fluorine coming out, bromine going back, chlorine to the right, hydrogen down. So that would be the way it's drawn in the figure. If I put the hydrogen back, we get 1, 2, 3. This is also clockwise, so the third and fourth options are the ones that are our configuration. So this is why I highly recommend that you do it with a model, or you use a modeling kit. You're free to use those during the exams, but that definitely keeps you from doing what I just did, which is just constantly confusing which atoms are where in space. So yeah, for 37, at least on my end, it's the last two that are our configurations. It's all just multiple choice. Because definitely, even the best software out there gets finicky about where you put your cursor when you draw things. So they're all equally weighed. So that's kind of what we're going to count for partial credit for an online course. Easy questions weigh just as much as hard questions, even though the hard questions have more work. There's more places to make mistakes. So your easy questions weigh disproportionately more because you can't show your work. So test packet 1, material page 15. Make sure that, so the numbers you're missing, make sure they're not in the table above it. Oh, wrong test 1 packet. Yeah, alpha glucose is in the table above it. Camphor, cholesterol, morphine. Glucose. So yeah, the numbers for the optical activity, the alpha Ds, those are all found on the table above it. How far off were they? Were they off? If it's like off by less than 5%, it's probably just rounding errors, or at least when the key was developed. By a good margin. So by a factor of 10. So 0.11 grams of alpha camphor dissolved in 100 mLs of water. And put in polarimer with a path length of 2.00 centimeters, and we want to know what the observed rotation is. So alpha D, in this case, is given to you. It's 44.26. So use format alpha equals alpha D times C times L times EE. In this case, we're going to treat EE as 100%. Path length 0.2 decimeters, so 44.26 times 0.119 divided by 100 mLs. So let me boot up Excel. Let me see what the key looks like. There's a good possibility the key's off. Particularly if you ever see like factors of 10 or 100. All right. Wow, I played myself on that one. Yeah, for the first one, it should be 0 because it's a racemic mixture. Racemic mixture has an EE of 0. That's amazing. So you have the camphor one beneath it, number 2. You have 1 gram of camphor. Ten mLs of water. Path length of 1 centimeter. Need 11, alpha is 11.2 degrees. One gram of sorry, making sure I'm reading it right. So alpha equals alpha D times C times L, and we're going to treat the E here as 100%. So 1, alpha here is 11.2. We don't know what alpha D is. C is you have 1 gram per 10 mLs, and a path length of 0.1. See, I'm getting 1,120. I'm thinking that this is actually supposed to be right there. The alpha is supposed to be 0.112. So I think it's just a typo and problem. Yeah, I think it meant to say the activity is 0.112, and that will give you an optical rotation of 11.2 for the reference for the third one. And then 1 gram of camphor, 10 mils. Sorry, shifted the page on me. You're getting 9.85 and it's 8.85. I wouldn't doubt that that's just a typo. That's supposed to be 9.85 in the problem. So let's see here. Equals 7.08 divided by 0.2 divided by 44.26 times 10. Question with 56. So this one was one I answered earlier, and it talks about which one would give you 105 versus 119. The thing here is that difference 119 corresponds to a CH2 group, and there's only one molecule in there that has a CH2 group to lose. So in this case, the B compound is the peak that has the 105 because it loses that CH2 on fragmentation, whereas A and C don't have a CH2 group to lose. So they're going to be the ones that are the peak at 119. All right, so that's the end of the live streams. I will try to keep my eye on my phone this weekend, but that said, it is a weekend, so if you're taking the exam and have issues, it's better to email me sooner rather than later. And I will see, hopefully, y'all Monday. We're supposed to get some snow Sunday, but I'm seriously questioning if it's going to be any more than slush. So ideally, I will see you Monday, but keep an eye out for any emails in case labs get canceled next week.